couple times during our lesson and during our review, we've talked about the whole stopping potential, the potential required to stop an electron that's already been ejected. And I've told you that later on, I'd explain to you why you might want to stop an electron that's been ejected. Well, that later on is coming now. I want to take a look at a quick little experiment and then the results we get from that quick little experiment and what that can lead us to, all right? You see up on the board here right now a power supply, which of course, just like the power supply we used in our in our current balance experiment. This power supply is connected to an ammeter. An ammeter, by the way, measures electric current. So most ammeters you see now are digital as opposed to with a little needle, but this one has a needle, and the needle goes, you know, to the right if there happens to be a current, and it gets buried to the left if there happens to be no current. Just tells us whether there's electric current present or not. Yeah, it's measured in amps. Yep. So it's the symbol I measured in amps. And then we have this evacuated tube, which just means a tube that has all the air sucked out of it, all the gases sucked out of it, with two electrodes. Right here, a positive electrode and a negative electrode. And that just means that the power supply is set up like this, right? It's like a battery that's set up with a positive side next to the positive terminal and the negative side next to the negative terminal. Now we've got photons that are coming in and striking this metal surface right here, this negative electrode right here. And these photons that are coming in are above the threshold frequency. So their frequency is above the threshold frequency. And when that happens, when we have photons that are above the threshold frequency, then we're going to get electrons that are ejected. Right? We'll get photoelectrons. One photon above the threshold frequency will cause one electron ejected. With the picture that we see here, looks like we must have had 3 photons above the threshold frequency because we have 3 electrons that are being ejected here. All right? So we fire photons in at a certain frequency that is above the threshold frequency. We get electrons that are ejected, and those electrons that are ejected end up being attracted to this collector right here. Agree? And then they start going around here, and they form an electric current. And what happens to the ammeter? You get a measurement of electric current in the ammeter, right? Okay, we haven't found anything really yet, but we're almost there. What happens if we take almost the exact same apparatus, but we flip around the power supply? What happens if we flip it around like this? Well, then this collector becomes what? Negative. And this surface over here becomes positive. All right. So now we got a photon. Let's say we got 1 photon coming in that's above the threshold frequency, barely above the threshold frequency, but above the threshold frequency. This photon comes in and causes an electron to be ejected, and this electron bounces out like this. But wait a second, it's no longer attracted to this collector, it's repelled, right? Now we got a potential difference that is going to slow down and stop the electron that's been ejected. In other words, now, if we apply the right potential difference, then we've got the stopping potential. So how do we know if we apply the right potential difference to stop the electrons? We can't see the electrons, right? I can't look at this with a microscope and see the electrons that are ejected and say, oh, wait, oh, that one's stopped. Okay, we're good to go. We can't physically see when the electrons are stopped. So how do we know when the electrons have stopped? Because the ammeter reads 0. Right? There's no current going around this if the electrons have stopped. So whenever we turn up our power supply to the point where the current reads 0, then whatever potential difference we have on the power supply must be our stopping potential. So look at the data that we have right now. We've got a frequency and we've got a stopping potential. What do you think is going to happen next? We have a frequency of photon that caused an electron to be ejected, and we have the potential difference at which we stop that electron. What are we going to do next? You guys know enough about lab work and experimentation that you know what's going to happen next, right? Think logically about this, okay? we shone a certain frequency, and then we saw what stopping voltage we needed to stop that electron. What are we going to do next? Change the frequency, manipulate the frequency, get a new frequency. And then what are we going to see from that? A new stopping potential. And then another frequency, and then a new stopping potential. We're going to end up with a table that looks like this, right? Frequency and stopping potential. What are you going to do with that table? Graph it. Probably graph it, right? A lot of times what we actually do is create a new table first, frequency and EK max, as opposed to stopping potential. EK max just comes from QV stop, so it's pretty easy to find, right? But not always. Sometimes we just graph these two variables. I'm going to show you a couple of graphs here. The first one being this graph, because far and away, this is the most common one that we see, F in EK. Yep. So let's say we got this data right here for frequency and EK max. EK max, which remember came from QV stop. Remember our original data table was frequency and stopping potential. We converted stopping potential to EK max, and let's say this is what we end up with. Doesn't matter if you guys write down these exact numbers, guys. Okay, it's the principle here that's important, not so much the numbers here. So if you don't want to write down those numbers, that's okay. We're going to plot a graph, and it's going to be a graph of what's going to be on the y-axis here. What's going to be on the y-axis here, Jacob? EK max, good. And what's going to be on the x-axis? Well, it's got to be the other one, right? The frequency. The y-axis is always our responding variable, and the x-axis is always our manipulated variable. Now, when we plot this graph of EK versus frequency, we're going to end up with a graph that looks like this. It's a straight line, but it's a straight line that doesn't go through the origin. Is there a y-intercept? Yeah, there is actually. You can't see where the y-intercept is here because it's going to be down here somewhere, right? But it still goes through the y-axis somewhere. So it's a little bit tricky. Okay, a little bit tricky. It's not like most of the analysis that we've done before, but that's okay. We can deal with that. What are we going to find from this? Well, let's see what we're going to find from this. We don't have to know exactly what we're going to find from this before we start our analysis. What do we do first? What do we do first? Now that we have a graph that is a straight line, what do we do with it? Or? Good. We get an equation from the graph. And this is a straight line graph, so it's going to be y equals mx plus b. Every time we have a straight line graph, that's exactly what we do, right? Now what? You guys are at the point now where you should be able to guide me through this. Okay, we've done this enough times, not for this graph, but for graphs in general. You guys should be able to guide me completely through this. What's next? Even before the formula sheet, right? We can't match up an equation from our formula sheet with an equation from our graph when we don't have anything other than the generic y equals mx plus b, right? We have to tailor that, right? So how do we tailor it to this graph, Nick? All right, so you got the slope and the y-intercept. Let's say we know what those are. Okay, let's say we know what those are. Now what? Q? Good. Replace y with EK and replace m with, we're going to replace m with the word slope, and x will be frequency plus b, right? We can't get rid of the b, the y-intercept, because there is a y-intercept here, right? Now, Jacob, what do we do? Coming back to you, because I know you know the answer to this. Yeah, usually it comes from your data sheet. Usually, you might not find that this time on your data sheet. You might have to come up with it on your own. What equation has frequency of light and EK in it? Frequency and EK. Think from your data sheet. Think about everything you know about the photoelectric effect. Yep. Good. HF is equal to EK plus W. Now let's rearrange that, right? Take the same form, solve for the same variable. EK ends up being equal to HF minus W, right? Now what are we going to do? We've solved for EK in both cases, right? Now we're pretty much done, right? We've done the hard part. Down, what do you want to do here now? Okay, so let's cross off what? What do you want to cross off then? Good. Cross off EK because it's the same in both. Good. And what else do you want to cross off? Good. Because it appears in both. And what are we left with? Well, we got the slope here is equal to Planck's constant. Hey, maybe this lab was about finding the value of Planck's constant. Carrie, what else we got? B is negative W. Yeah, B is, the y-intercept is the negative of the work function. That make sense? Do you see what you've done? Okay, you've never even remotely thought about this graph, let alone actually use this graph to find anything. But yet, you guys just guided me through the process of figuring out what the slope means and the y-intercept means. Now, there is one thing that's conspicuously absent from this right now, from this experiment, and that is the threshold frequency. There's two ways that I can find the threshold frequency from this graph. One is just to look at it and say, hey, the threshold frequency is the x-intercept. Okay? Look, at this frequency, that's when electrons begin to be ejected and have a kinetic energy. So we can say the x-intercept is the threshold frequency. But if you don't catch that, because it doesn't really follow our general strategy of analyzing the graphs, right? You just kind of have to kind of catch that. If you don't catch that, then the other thing you can just say is, well, look, we found W from the y-intercept. We found H from the slope. We can calculate the threshold frequency by saying it's the y-intercept over the slope, right? There's a couple ways you can deal with the threshold frequency there. That make sense, Nick? Sorry, say it again. Sorry, I didn't understand that. Oh, okay. So how do I know to replace y with EK instead of y with F? Okay, because the y-axis is EK and the x-axis is F. Okay, good question. Sometimes we have set like a really simple question like that, you know, like the easiest part of it, but if we just, I don't explain that as well, maybe because it's the easiest part of it, and maybe we're missing that because I don't explain it as well as some of the other stuff. So it doesn't matter how simple the question seems, ask that question, because I mean, that makes me more conscious of that too. So this afternoon, I'll pay more attention to that when I'm teaching the kids this afternoon. That make sense? I want to show you something here now. Okay, this is a slight little aside, but this is an aside that I want you to use come diploma exam time, okay? I've told you a million times, you will get at least one grafting question on your diploma exam. You will have to do this for sure. Now, when we've done this with labs, we've always got our value of the y-intercept and the slope by Google Sheets, right? It always spits it out for us. You're not going to have Google Sheets on diploma exam day. So how are we going to do it? Well, you could do it the old-fashioned way. Slope is equal to rise over run and whatever. Do not do it that way. Okay, that is almost obsolete using that method. Here's what I want you to do right now. Everybody take out your calculators right now. Everybody take out your calculators. Okay, some of you may know how to do this already. Most of you will not know how to do this already. I'm going to give you a simple way of finding the slope and the y-intercept of this graph using your calculators. Everybody has to follow along, and everybody has to enter the keystrokes in here, okay? Because we want everybody to be able to do this. So turn on your calculator. We're going to start entering some data here. Hit the button that says stat right here. Okay, hit stat. And then you're going to have all kinds of options. You're going to click the very first one, edit. So hit stat, enter. And you're going to see a table that looks something like this. It should be blank. If it's not blank, then just go through each of the places that has numbers in it and delete them. Do not delete a column. Do not go up here and delete. Okay, you want to keep L1 and L2. You want to keep those columns. But it's okay to delete data. You will almost certainly not have data in here already, but if you do, just delete them. On diploma exam day, you certainly won't have data in there because your calculator is going to be cleared for you, right? So it's going to be all blank. Okay, so let's enter this data. 5.2, this is column 1, 5.4, 5.7, 6, yeah, you hit enter after each one, yeah. Or I think you can just press the down button as well, whichever. 6.3, 6.8. Yeah, you can just hit that down button as well. And 6.9. Okay, there you go. My first column is entered. Let's scroll up and do my second column now. 0.0528. We've got 0.1356. We've got 0.2598. 0.5082, 0.7152, and 0.7566. Doing it this way guarantees you're going to get the value that they want you to get on the diploma exam. If you do it using slope is equal to rise over run the old-fashioned way, and you're off by the tiniest little bit with interpreting your points and whatever, like you could be off by a little bit. You don't want to do that. You don't want to do that. You want to do it this way. All right, so we still don't have any numbers, though. We still don't have any slope or anything from this. Everybody get that entered? If we do, okay, now it's time to get the slope and the y-intercept. Now I want you to hit stat again. Remember, we started this off hitting stat. We hit stat, edit, and then entered our data. Now we're going to hit stat, calc. We want to calculate something. And we're going to scroll down to option 4, which says linear regression. LinReg, linear regression, AX plus B. Press enter. Press enter again. And look at what happens. It tells me my equation is y equals ax plus b. A is 0.414. B is negative 2.1. My slope is 0.414. And my y-intercept is negative 2.1. I don't even need to see the graph. Okay, I've got my slope and I've got my y-intercept. If you used Google Sheets, it would have given you the same values of the y-intercept and the slope. Does that make sense? Is that easy to do? Or is there a question there? Oh, sorry. What calculator do you have? Is that the 84? Okay, so you have to hit enter a few times. Okay, and I think actually on that one, actually it says, it's in the form of y equals, it says b plus ax. Or does this? Oh, it does? Okay. There was one calculator that I saw that says b plus ax. Or I think it was a plus bx. And why it said that, I don't know. But in the end, the one that's attached to x is your slope. Whatever they call it, a or b or whatever, right? So I had to press enter twice, but mine's an 83. Maybe you have to press enter 4 or 5 times, but you'll get there. Is that okay? Sorry, on math? Yeah, sure. It's a built-in function for your calculator. It's allowable calculator. So I don't see any reason why you're not allowed to do that on your math test too. Guys, one more thing. Here's what often happens on your diploma exam for that graphing question. They will often give you a graph that looks like this with the line already plotted instead of a data table, right? Because they can't expect you to plot the graph. They want you to see the graph. So they're almost certainly going to give you the graph. Maybe they give you points like this, and you have to enter those points in to your calculator, or maybe they just give you a straight line like this. What should you do if they just give you a straight line without any actual data points? Oh, it's easier. Because then you got two data points. You got this one, and you got this one. Then all you got to do in your calculator is enter the first point and the last point. If it's a perfect straight line, first point and last point are fine. If it's a line of best fit that they draw for you, or that they expect you to draw, then you've got to use all of your actual data points. That makes sense? Yeah. Like where they give you, yeah. No, you don't have to draw anything. Now, that's the thing. They used to give questions where they just give you the points, no line of best fit drawn, and they'd say, well, figure out what the slope is. And a lot of people would take a ruler, draw a line of best fit, and calculate the slope using the old-fashioned way. And it's like, no, like if you're off by the tiniest little bit on your line of best fit, like you're going to get the wrong answer. Like, and how easy is it to be off on a line of best fit, right? Enter the points in your calculator. It'll give you the exact value without even having to draw the line of best fit, right? Okay, I'm going to show you one more graph here. And we're going to go through that analysis too, okay? Just real quickly here. What if we hadn't gone frequency and kinetic energy? Remember our original data was frequency and V stop? Remember that? What if we had just plotted that? What if we had a plotted frequency and V stop? Yeah? Not exactly. We'd go through the same strategy, but we'd say Y equals mx plus b. Y would be what, Nick? Yes. M would be slope. X would be frequency. And B would be Y-intercept, right? Come up with an equation that has those variables in it, F and V stop. Well, it's going to be HF is equal to QV stop plus the work function. So it's a little bit trickier equation to come up with, right? Really, it's kinetic energy plus the work function, but we're replacing kinetic energy with QV stop. Rearrange it to solve for V stop. It's equal to HF over Q plus W over Q. So subtract W over Q. Take the W over by subtracting, and then divide everything by Q. So what do we get here? Cross off V stop, cross off F. I've got slope is equal to, what's the slope equal to? H over Q. What's the Y-intercept equal to? Negative W over Q. And what's Q? 1.6 times 10 to the minus 19, the charge of the electron, right? So it's a little bit uglier, but whatever, right?